In the last lecture, we saw that we can have a variety of different crystal types or crystal lattice types, and they have different properties. The BCC lattice, the FCC lattice, you have the zinc blende structure, the diamond lattice, and so on and so forth. And we classified, and different materials can be put into these different lattice types. Now, why is it important to analyze these different lattice types? As you will see later on, depending on the nature of the lattice type, if you have atoms which are arranged on a cubic lattice, okay, then depending on the type of lattice that you can have one big atom in the center, okay, and the electrons in these atoms could be delocalized. Okay, the electrons in the atoms are not always around the ions which are present or the positive ion core which is present. Sometimes if you have an F shell electron, they could be delocalized, they could be wandering much further than the nucleus, okay, far away, they can move to distances much far away from the nucleus, the D shell electrons and so on. And depending on the lattice structure, you can have overlapping of orbitals along certain particular directions in the crystalline structure. So, along certain directions the overlap might be strong, and along certain other directions the overlap might not be strong. That will immediately affect the electronic properties of the material. So, they have an immediate effect on something called as the band structure of the material. So, depending on the crystal structure and how the electrons are overlapping and delocalized along the lattice, you can have different types of behaviors of the bands inside the solid, which are governed ultimately by the nature of the crystal structure. Depending on the crystal structure, the overlap of the electrons along some directions might be much more than compared to other directions. Similarly, depending on the crystal structure, so this will affect electronic properties. Crystal structures immediately have a role to play on the electronic properties. The electronic property could become highly anisotropic. Along some direction there is more overlap, some directions there is no overlap at all or partial overlap. It can affect, this itself can affect magnetic properties, because depending on the overlap of the wave functions with spins, you can have ferromagnetism, you can have exchange interaction, something called as an exchange interaction along some directions and not present along the other directions and so on. So, the symmetry of the crystal structure or the nature of the crystal lattice that is there governs the properties of those materials, the electrical property, the magnetic property. Similarly, depending on the crystal structure, certain types of vibrations are possible. Vibrations along certain directions are more probable than along different other directions. For example, vibration along the diagonal might not be so pronounced, but vibration along these might become more pronounced in certain types of crystals. It varies from crystal to crystal, one cannot generalize, but the crystal structure actually makes also the vibrations of these atoms very different. And therefore, when you find the specific heat of the material, which has contributions of course from the electrons inside the material as well as contributions from the vibrating ions, something which I have told you earlier, then the net specific heat of the material, mostly the vibration of the ions, actually is very different. The acoustic properties or the vibration properties of the material depend on the nature of the crystal structure. What is the type of the crystal structure controls all these different properties. So, therefore, what is the crystal structure is very important. It is an important ingredient which will go into understanding some of the properties which I have told you, namely the electronic property, magnetic property, the vibrational property. Till now, when we looked at the Drude's model, the Sommerfield's model, and when we looked at the electronic, magnetic and vibration and the specific heat of the electron, we did not look at the vibrational properties, but we looked at least the specific heat of the electrons. Nowhere did we introduce anything about the shape of the lattice, but now that is why there were quite a few drawbacks, it could not explain many of the things. But now once you have a way to analyze the lattice and the tools that have been given to you to analyze the lattice, you can use it to understand how the electrical properties change and what new things start emerging to explain features which were not explained in the earlier theories, because they did not take into account a presence of a underlying lattice which has a particular very definite structure and electrons are interacting with that structure in the lattice. So, it is indeed very important to define and understand the crystal types and study their properties. Now, another very important thing, another important tool, till now we have been using various tools to analyze the crystal structure, namely the primitive lattice vectors, the primitive cell, the primitive volume, the unit cell, the conventional unit cell. All these are tools, the symmetry properties, all these are tools to understand the lattice structure. Along with them, one can ask another question, that if you have a lattice of points, a simple lattice in 2 dimensions, I can define different planes of atoms. Okay, I can define a plane of atoms. Okay, and these planes are all parallel to each other. One plane of atoms that I can define is like this, okay, and I can go on. Okay, I can define planes of atoms, or I can define another plane which is along this direction. Okay, I can define planes of atoms which are along other directions, and so I can define many different types of planes. Okay, I can define these vertical planes where I will have lattice points sitting on those planes. So, inside a lattice I can define many different planes on which I will have lattice points which are sitting. Is there a way to classify and categorize different types of planes in the lattice? And that brings us to the topic of indexing crystal planes. So, in a 3 dimension, I showed you in a 2 dimension there are different types of lattice planes I can define, some verticals, you can define horizontal lattice planes. If I have these set of points, of course, then you can define horizontal lattice planes, vertical lattice planes, I can define those at an angle, and each of them will contain lattice points or atoms on them. Okay. 3 dimensional lattice crystal planes will have, you can have these parallel set of planes which will contain lattice points. These are, for example, in a cube you can see these points which are at the corners of the cube, and for this blue color lattice plane you have these 3 points which are sitting on them, and similarly I can define a parallel set of points for this plane which is along this direction. I can define another plane where I have these 4 points which are sitting along this plane, and similarly there are a parallel set of planes. I can have another set of planes which are like this. What distinguishes these different planes? What is the way that I can identify, and each of these planes actually collects a certain set of atoms, okay, along certain direction. These planes are oriented along certain directions. Is there a way to classify these different planes? Namely, if I give you a certain number or if I give you a certain quantity, then I can immediately say that I am not talking of each of these planes, but I am talking of all these planes. Okay. So, just with one particular combination of numbers, is it possible to define certain types of planes, and therefore come up with a way to define any type of planes in the system. And whatever we will do, we will not do an indexing for this plane, for this plane, for this plane, but if I come up with a scheme of indexing, it will define all the planes which are parallel to each other. For whatever indexing I do for this plane will be the same for all of these planes. Whatever indexing is for this plane will be the same for this, similarly for this. And this procedure of classifying planes is called the Miller's indices, and it will become very useful as we go along for classifying lattice planes and planes of atoms inside a solid. So, for now I will just give you what is the procedure for finding a Miller's indices associated with a plane. So, suppose you have a crystal, this is the lattice plane of a cubic crystal, but suppose the crystal is not cubic, it is distorted, then you have 3 directions with the fundamental lattice constants which are A1, A2, A3. In a cubic crystal, the lattice constants are all A. If you recall, for a cubic crystal the lattice constants are all A, but if I distort the crystal along the 3 directions, then I can in general talk of A1, A2, A3. And let us talk of a lattice plane, which is this lattice plane of atoms, which is shown here as this plane, which is sitting inside the structure. If A1 equal to A2 equal to A3, if A1 equal to A2 equal to A3, then of course I have a cube. Then this is a cube and these points are sitting at these 3 corners of the cube, and this is the lattice plane. But in general I am taking that A1 not equal to A2 not equal to A3. Then how do I define, how do I index this plane? What you first do is that find out the intercepts along the axis. These axes can be the primitive axis or the axis of the conventional unit cell. So I first find out the intercepts of this plane along the 3 axes of the system, and these axes could be either primitive lattice vectors or vectors along your conventional unit cell. There is no restriction, conventional unit cell, but whatever you define you have to stick to it. Okay. So for the cubic cell, of course it is very easy, your primitive unit cell and the normal ones, your conventional and the primitive are both identical. Okay. So along these 3 axes, which are the fundamental translation vectors of your lattice, okay, it could be either primitive or non-primitive, namely along the conventional unit cell, you find the intercepts. So A1, and you write it in terms of the lattice constants. These are the lattice constants. So if the intercepts are x1 A1, x2 A2 and x3 A3, okay, these are the intercepts. For example, in this example, this intercept is 3 of A1, this intercept is twice of A2 and this intercept is twice of A3. Okay. So I first find the intercepts, then I take these values and I take their inverse. Okay. I take the inverse of the intercepts which are written in terms of the lattice constants. After I take their inverse and find out 1 by x1, 1 by x2, 1 by x3. So I find out 1 by 3, 1 by 2, 1 by 2. These are the inverse of the intercepts. Then I have to find out what is the smallest integers HKL, the smallest set of integers HKL whose ratios are exactly identical to the ratios of these intercepts. So I have to find out the ratios of the intercepts, inverse of the intercepts. What I do is that I can multiply it by the least common factor for them and I will get intercepts 2, 3, 3. These are my HKL. Okay. So if I do this procedure, then I will find out a unique index which is indexed by this collection of HKL integers. The HKL integers, H is equal to 2, K is equal to 3 and L is equal to 3 in this particular example. These index not only this plane but all the planes which are parallel to this plane. Okay. All the planes in the lattice which are parallel to this plane are all indexed by this unique number 2, 3, 3 HKL, and these HKL are called Miller's indices, and this gives a way to index different lattice planes along different directions in the crystal. For example, if you have this lattice plane, okay, shown here, it has an intercept along A. If A is the intercept along this direction, it is a cube, okay, but the intercepts which are along the x and y are infinity and along the y direction are infinity. So intercepts of this plane along the x and y are infinity, but along the z direction it is finite. So the Miller's indices for this plane is 0, 0, 1. You remove the comma. Okay. The Miller's indices H is equal to, this is of course 1 over infinity, it will give 0, 0 and 1. So, this is taken as the 0, 0, 1 plane defines all the planes which are cutting the z axis and parallel to the xy plane in the cube. 1, 0, 0 is of course this plane, it has no intercept along the z axis, but intercepts of A and A along this. So, this is the 1, 1, 0 plane, and similarly the 1, 1, 1 plane is for a simple cube, there are 3 intercepts, okay, and this is your 1, 1, 1 plane which is going along the diagonal of the cube. So, if you have a cube and a plane which is along the diagonal of the cube, okay, so you have a plane which goes along the diagonal of the cube, then that is your 1, 1, 1 plane which you can define, and with this you can identify different set of lattice planes and index them. You do not have to write an index, or when you want to talk of a lattice plane, you do not talk of this individually, this individually, this individually, but you talk of an HKL lattice plane which immediately specifies what is the orientation and direction of that lattice plane. So, this becomes a way to actually analyze crystal structures, and we will continue now to understand some of the properties of these crystals as they diffract light or electromagnetic waves. And here use of these indices will become very essential, which we will continue in the next few lectures.